So in this video, we're learning all about synthesis reactions. And synthesis is when you take two or more reactants, squish them together, and you form just one product. So if you are making a single product, you're doing a synthesis reaction. There's a bunch of different synthesis reactions. These are the ones we'll focus on. If you have an ionic compound as your product that you're trying to form, well, you guys know already that an ionic compound is formed by combining a metal with a nonmetal, right? That is what an ionic compound is. It's a metal and a nonmetal. So to synthesize it, the reaction we do is really straightforward. We take the metal, we add the nonmetal, you get an ionic compound. Same idea with a molecule or a molecular compound. You know that a molecular compound is made of two or more nonmetals. So the synthesis reaction is just going to be take the components, take the nonmetal, take the other nonmetal, add them together as the two reactants, and you get the molecule. Then we're going to start to learn some slightly trickier synthesis reactions. How do you synthesize an acid? Well, one way to synthesize an acid is take a nonmetal oxide. So an example of a nonmetal oxide would be like sulfur dioxide, right? So sulfur is a nonmetal. Sulfur is a nonmetal here, and oxygen is the oxide part there. If you add that to water, you're going to get an acid. I'll show you some examples of that. The other interesting one that we're going to learn about in this video is how do you make bases? So a base would be something like maybe calcium hydroxide, right? It's that OH thing that clues us in that this is a base, the hydroxide group. There's calcium hydroxide. Well, how you do it is you actually add together a metal oxide. So like calcium oxide, that would be a metal oxide. It's a metal like calcium bonded to oxygen. That makes it a metal oxide. So oxide just means bonded to oxygen. Plus water, that will form that metal hydroxide or the base. I'll show you an example of that too. So starting with the simplest ones, to make an ionic compound, let's say you wanted to make copper 1 chloride or maybe copper 2 chloride. Those are simple ionic compounds. So to figure out what reactants I would need to add together to synthesize that, just split it into the two things that are there. So copper 1 chloride is made of copper, which is a solid, and it's made of chlorine. Now here's where you want to watch out. If you have one of those diatomic compounds, so remember the hockey stick and puck, hydrogen, oxygen, chlorine, those guys, fluorine, those ones, when you're adding them together as elements, and when they're just on their own as elements, like chlorine on its own as an element, it'll always bond to another chlorine. It'll make Cl2. So I'm not just going to take copper and add it to a single chlorine. I'm going to take the copper and add it to a Cl2 in order to form my copper chloride. So the reaction looks like this. Copper chloride has the formula CuCl, right? Because copper 1 has a charge of 1. Chlorine has a charge of -1. So we get a 1-to-1 ratio there, CuCl. But the two reactants that add together to form that are going to be copper here, and chlorine gas, which is Cl2, because it's diatomic and it's a gas. This one's really pretty, by the way. I'll just balance that. I should do that. So I need a 2 in front of my copper chloride, right? Because I've got 2 chlorines here, and I need a 2 in front of the copper now to balance out the coppers. I'll show you what that one looks like. It's really pretty. It's like kind of a green salt. Copper 2 chloride, exactly the same idea, right? It comes from copper, which is a solid, and chlorine, which is a gas, and it's Cl2 because it's diatomic. And it forms CuCl2, right? Because in this case, copper has a charge of 2 and chlorine has a charge of -1. So that's going to give me 2 chlorines for every 1 copper. And it actually looks quite different. It's a really beautiful teal color when you make copper 2 chloride. So those are how you synthesize an ionic compound. Just add together the metal in the ionic compound and the nonmetal. Watch out for diatomics. So that's the only sort of thing to be aware of really there, and you're good to go. The other pretty straightforward one is how do you synthesize molecules or molecular compounds, especially simple ones that just have 2 elements in them. So carbon monoxide would be an example of that. Carbon monoxide is just CO. It's a gas. It's a dangerous gas. We'll learn more about it later in our unit when we learn about combustion reactions. But it's just one carbon, one oxygen, right? The mono means there's one oxygen there. If you think about what elements it came from, well, carbon, let's just see, and that's a solid at room temperature. And oxygen is the other element. Now watch out again here. Oxygen is diatomic. So even though we're going for just one oxygen, right? Carbon monoxide only has one oxygen. When oxygen is alone, when it's just an element by itself, it's going to find another oxygen friend and bond up and make O2. So we're going to be combining O2, and it's a gas as well, right? That will form carbon monoxide. So the reaction looks like this. Carbon solid plus oxygen, O2 gas, forms carbon monoxide. And of course, I'm not done until I balance it. I've got 2 oxygens on this side, so I'm going to need 2 oxygens out front here in front of my carbon monoxide. Now I've got too many carbons on my product side, so I'm going to need another 2 here in front of the carbon. And now it's balanced. Right, so those are our 2 simple cases, forming an ionic compound or forming a molecular compound. We're just going to take the components, either the metal plus the nonmetal makes an ionic compound, or nonmetal plus nonmetal makes a molecule. Now, how do you form acids? So one way to synthesize an acid is to combine a non-metal oxide and water. And a really cool case of this is actually carbonating beverages. So carbon dioxide, CO2, is a gas. So I'll put that gas there. It is a non-metal oxide, right? Carbon, that's a non-metal, and it's bonded to oxygen, which makes it an oxide. So an oxide, right, just means bonded to oxygen. Non-metal bonded to oxygen would be like carbon dioxide is a great example of that. When you carbonate a beverage, what you do is you just pump a bunch of carbon dioxide into the water, and you add, sugar and flavoring and whatever, and you get Pepsi or sparkling water or Sprite or whatever carbonated beverage you like. But anytime you add a nonmetal oxide to water, it actually forms an acid. And in the case of a pop, it forms carbonic acid. And that's what gives it that kind of zing flavor. So you know how if you eat a lemon is acidic, right? It's got that sour zing to it. That makes it lemon, I think, like tastier, right? It adds that extra bit of flavor. That actually happens with a carbonated beverage as well, right? So you add carbon dioxide to water, you make carbonic acid. That's why carbonated beverages taste so good. They have that zing because there's actually an acid in there, and that acid is carbonic acid. This is a reaction here written out. So carbon dioxide, a gas, we're going to add it to water, which is a liquid, and that will form carbonic acid. So it'll form the acid. Notice just a little pattern here. It's kind of like you can think about it as like the O from the water, just adds one more O. So if this was O2, it's going to become O3. Then you can recognize that as carbonate, and carbonate has a charge of 2, so it's going to need 2 hydrogens. Carbonate has a charge of -2, so it's going to need 2 hydrogens, which each have a charge of +1 to bond to it. So that's why we've got H2CO3 as the formula for carbonic acid. And if you look at your solubility guidelines, anybody bonded to H is going to be aqueous. Any polyatomic ion bonded to hydrogen is aqueous. So all of our acids are aqueous. So that's that reaction. We're going to learn a little bit more about this one because it's a really cool reaction, actually. One thing that's fun about it is it goes forwards or backwards. You're going to learn more about how reactions go both forwards and backwards in grade 12. You'll learn about equilibriums. But I want to show you something cool about this one. So when you carbonate a can of pop, as long as the pressure is high on the pop bottle or the can of pop, that reaction will tend towards forwards. So it has this more of a tendency to form the carbonic acid. Then the carbonic acid has a tendency to go backwards and reform carbon dioxide gas and water again. So that will always happen, right? It can always run both forwards and backwards, but it'll tend towards going forward. So you'll make more carbonic acid in there and it'll have that nice zingy pop flavor. But once you take the pressure off, so once you open the pop bottle or crack the pop can, now the reaction will actually tend towards backwards. So that means you're going to be forming more of this water and carbon dioxide gas again, and less of your carbonic acid. So the carbonic acid will be reforming the reactants, the water and the carbon dioxide. That's why your pop goes flat. So the carbonic acid comes out, it reforms the carbon dioxide gas, which comes out of solution. It bubbles out of your pop and drifts off into the atmosphere. And your pop now just tastes like water. Like it's no longer this nice carbonated feeling, right? It doesn't have that zing anymore. It loses its carbonic acid. Um, it's a pretty cool reaction. If you want to speed up the going backwards part, there's one way you can do that, which you may have tried before, and we will try in our class because it's really fun. If you take a Mento happens to be covered in tiny little pores and pits and peaks on it, right? So Mento, it looks really smooth if you look at a Mento, right? But actually there's all these little tiny bumps on it. And those are caused by the fact that when Mentos are created in factories, what they do is they just sort of like airbrush sugar onto them. They take sugar, little tiny particles of sugar, and they spray it all over the Mento. It gives it its nice sugary flavor on the outside. But it also creates all these little tiny nucleation sites. A nucleation site is a place where a bubble can get started. And it just needs to be a little bump or pit or peak, just a little bump on your Mento. All those little nucleation sites can each form a bubble. And if you want to go backwards in this reaction, if you want to take your carbonic acid and go backwards to reform carbon dioxide gas and water, then the way to do that is you need bubbles, right? Carbon dioxide gas comes out of solution as a bubble. So what you need is a nucleation site, and Mentos provide tons and tons of those little nucleation sites. And so they can allow this backwards reaction to happen faster when the pressure is off of a pop can. So you want your pop to go flat really fast, stick a Mento in, you'll form tons of bubbles really fast. Bubbles also have a thing, which is they beget other bubbles. It means that once bubbles get started, then that makes more bubbles start from the bubbles. So as you kind of get that bubbling going, it bubbles even faster and the reaction speed increases exponentially. All of those CO2 bubbles will explode out of the top of your bottle, and that is why if you stick some Mentos in Coke, you get a big spray of Coke going up in the air, which is pretty fun, and lots of CO2 gas quickly being released from your Coke bottle or whatever carbonated beverage you use. This works with any carbonated beverage. It's a fun experiment, definitely one you can try at home. It's very safe. Another example of a non-metal oxide in water is burning fossil fuels. So this is not as fun of an example. When you burn fossil fuels, it creates a lot of CO2. So this is just when you drive your car, when any action that burns fossil fuels, you create a lot of CO2. You also create a lot of SO3, so sulfur trioxide. That gets released into the atmosphere, and that can actually create acid rain. So it actually forms an acid when it bonds to the water in our upper atmosphere. That acid might be carbonic acid if you're talking about CO2, or sulfuric acid if you're talking about SO3, and then that can actually fall down to Earth in the form of acid rain. So here's what that reaction looks like. So notice again this thing with the oxygens, right? If we have sulfur trioxide, we'll tend to form like an SO4. SO4, we know you recognize that as a polyatomic ion, right? It's a polyatomic ion with a charge of -2. And hydrogens each have a charge of +1, right? So that's why we're going to get 2 H's with each SO4 polyatomic ion. But notice SO3 makes SO4. It's like this water from the oxygen from the water gets added to the 3 oxygens here in the sulfur trioxide. So that's how we synthesize sulfuric acid. Just some interesting facts that I think are encouraging to know. So back in the early 90s, Sudbury's nickel plant was a place that was famous for releasing tons of sulfur emissions. So it created a lot of that sulfur trioxides going up in the air, bonding with water in the atmosphere, creating sulfuric acid. That was causing acid rain. And acid rain was causing a lot of damage and still does cause damage to buildings, causes huge damage to trees and lakes in our environment. But what's encouraging, I think, about this is that there started to be put some emission regulations on a lot of these big smokestacks where they had to put scrubbers on them, and those scrubbers removed a lot of the sulfur trioxide being released. That's actually saved a lot of our lakes. So back when I was in high school, I remember, I'm very old, so I was in high school a long time ago, and I remember learning all about like, oh man, acid rain, it's going to kill all of our lakes. And that's actually not as big of an environmental problem now as it was when I was in high school. And that's really thanks to a lot of these environmental regulations. So I think that's pretty cool. Last but not least, how do you form a base? A base is formed very similar to an acid, except for instead of a non-metal oxide, we're going to use a metal oxide here. A metal oxide and water will make a base. So let's say you wanted to make sodium hydroxide. Sodium hydroxide is very handy. That's the thing we used in our first titration lab. We titrated sodium hydroxide with HCl. It's also really useful for making soaps and detergents and all kinds of things. So say you want to synthesize it. Sodium hydroxide is NaOH, right? The sodium and then hydroxide is OH. They each have a charge of 1 and -1, so 1-to-1 ratio, NaOH. The metal oxide that you use to synthesize sodium hydroxide will be sodium, so the same metal in the base, bonded to oxygen. So it'll be sodium oxide, so NaO. Now watch out for your chemical formula here. Sodium has a charge of +1, oxygen charge of -2, right? So I'm going to need a 2 here. 2 sodiums for every 1 oxygen will work. So this reaction will be sodium oxide plus water, so our metal oxide plus water will make the sodium hydroxide the base that I want. Writing down my formula, sodium oxide is Na2O, so we said it's a solid. We're adding it to water, which is a liquid, and that gives me sodium hydroxide. I know from my solubility guidelines that sodium, that's in group 1, it's aqueous with everybody. So this is going to be dissolved in my water. And you saw that in the lab, right? The sodium hydroxide that you used in the burette, that was looked like a clear liquid to you, right? Like it was fully dissolved, totally aqueous there. And that is how we form a base from the metal oxide. Double check that it's balanced. I see I've got 2 sodiums over here, so I'm going to need a 2 out in front of my sodium hydroxide. Hydrogens, I've got 2 hydrogens now here, and there's 2 hydrogens here, so that's all balanced. Oxygens, I've got 2 in the sodium hydroxide, and I've got 1 in the water, 1 in the sodium oxide, so it's balanced as well. And that's how I make a base out of a metal oxide and water.